this top two, is that it? Did that work?
Yes, I can.
All right.
Think you're ready.
But now I need, okay.
Well, thank you everyone for your patience and welcome. We'll do the statistics seminar. We're very happy to welcome Po-Ling Loh from the University of Cambridge today. She will speak about differentially private estimation by noise optimization. Thank you for coming, Po-Ling. The stage is yours.
All right, thanks a lot, Stats. So I'm very grateful for being able to come here, especially on sort of short notice. So I'll be giving a talk that kind of touches on three different pieces of work. One is joint with Marco Avila Medina, actually two of them, who's at Columbia University, in the statistics department. And the first body of work is with him and a former PhD student at Columbia, Casey Bradshaw. That's published. Then the second work that's sort of been work in progress for a while now is with Marco and a former PhD student of mine from Wisconsin, Jung Liu. And then the third part is very recent stuff with my first year student, Laurencio Marcus. So I mean, I welcome comments, especially on the later stuff. And the goal is to talk about differential privacy and its interface with statistical estimation. Right. In case you have not seen differential privacy before, let me linger a moment on this definition. So differential privacy is a formulation of privacy that was that was invented around 2006. And what it says is that an algorithm A is private if when you apply it to a data set X and a neighboring data set X prime, where you change one entry arbitrarily, the output shouldn't change too much. So usually privacy is parameterized by either a single parameter epsilon or joint parameters epsilon and delta. And these are going to be non-negative numbers. So in the extreme case, if epsilon and delta were 0, then we see that it says that by applying this definition to X and X prime in turn, it says that the output of the algorithm on X is constant. It's going to be absolutely the same everywhere. Okay. If epsilon and delta are a bit bigger than 0, it allows you to just have an algorithm that has a stable output that's not necessarily constant. And this might seem like a simplistic notion of, privacy, but the impact of this framework, of this theoretical framework, is quite profound. So starting in 2014, privacy was implemented by Microsoft, Apple, Facebook, and so on. So sort of the definition that has stuck from the last several years. And another basic fact about privacy is that if you add Gaussian noise to a deterministic function, provided the function has a certain bound on its sensitivity, then the output can be made to be private. So in particular, let's say you have some deterministic function f of your data. Now that in itself would not be private. But if your function has this sensitivity bound, which is that when you apply it to a data set X, a neighboring data set X prime, it changes by at most delta f. Then if you add Gaussian noise with variance proportional to delta f squared and inversely proportional with the privacy parameters, then you end up with an estimator which satisfies epsilon delta differential privacy. This is something that you can calculate just by looking at PDFs and sort of working from first principles. This is what's called the Gaussian mechanism, because it's a way of making a function private by adding Gaussian noise. You may also have heard of a Laplacian mechanism, and a Laplacian mechanism is to add Laplacian noise, and that's generally what people do if they want to ensure privacy that's just parameterized by epsilon with no delta. Sort of the initial formulation of privacy was just with a single parameter epsilon that governs how sensitive the algorithm is with respect to the input. And it turns out that if you add Laplacian noise with parameter proportional to sensitivity and inversely proportional to epsilon, then you can also get privacy in that sense.
So could you
Yes.
explain a little bit of why we're calling it privacy, and is it the same privacy we were talking about?
Yeah, so I mean, so it's called differential privacy because it sort of tells you what happens when you have a data set and you change one data point. Okay, so it's the differential of what happens when you have, so what it's supposed to do is that whatever output, so for instance, if you have like, the mean income of a certain population, then the guarantee is that whether or not you choose to release your data to the statistician, whatever is output, namely a noisy mean, shouldn't say much about whether you are in the data set or not. So that if someone then gets access to the data set, like, should they be able to know something about you or not?
Okay.
Now, it is very debatable whether or not this is a good enough definition. And I mean, in fact, I didn't work on this for many years because I wasn't quite convinced, but this is the definition that is currently used in industry. So, all right. And then another thing to say is, so that's the basic definition of privacy, where there are these epsilon delta parameters. In this work, I'm going to use a slightly different notion of privacy, and this is more recent developments from the statistics and computer science community. So it's called Gaussian differential privacy, and it was in a JRSSB discussion paper in 2022. And this notion that I'm going to touch on very briefly is based on a hypothesis testing viewpoint of privacy. So just like we want to protect, your information, whether you're in the data set or not, the hypothesis testing viewpoint is like, suppose you want to test the hypothesis of whether the underlying data set is some set X or some slightly perturbed set X prime, and how hard is it to do this hypothesis test? And in a paper that a JASA paper from 2010, Larry Wasserman and Shuheng Zhou showed that, perhaps not surprisingly, if you have a test which is epsilon delta differentially private, so what that means is that the test is based on a test statistic, which is itself differentially private, then that means that the power has to be upper bounded by something. Okay, so you can't do that well if it's going to be differentially private, because if it's differentially private, then it's hard to tell between X and X prime. So perhaps not surprisingly, for a significance level alpha, an epsilon delta DP test has a power that's upper bounded by some function of alpha, epsilon, and delta. And this idea was sort of generalized by the JRSSB paper by Dong et al. And in that paper, they said, well, okay, maybe you're trying to find some other trade-off function. So the trade-off function is sort of saying, for a significance level alpha, what is the power upper bounded by? And they generalized this to different sorts of functions. And one specific choice, which I won't go into in detail, leads to what's known as Gaussian differential privacy. So this is now parameterized by just one parameter mu, and then there's a mapping between significance level alpha and power upper bounded by a function of mu and alpha. And it turns out that, well, this Gaussian mechanism is particularly nice to analyze. And there are two facts that we will need moving forward. So the first is that under the framework of Gaussian differential privacy, there's also some notion of a Gaussian mechanism. So if you want to make a deterministic function private, where privacy is governed by mu Gaussian differential privacy, it suffices to add Gaussian noise, where the variance is proportional to the sensitivity of the function squared, and it's inversely proportional to the level of privacy. So that's the first thing, and the second one is that in differential privacy, there's been a lot of interest in understanding if I do something, if I apply a private mechanism, and then I apply another private mechanism where it's a composition. So I take the output of the first private mechanism, and maybe I look at the data again, and I calculate something else, and then I do something else. Then what is the overall privacy guarantee for these different steps that are individually private? It turns out that Gaussian differential privacy is a very nice composition, and the privacy is sort of tightly characterized by Euclidean norm. That's the second fact that we need to know moving forward. Okay, so differential privacy grew out of the theoretical computer science community. And much more recently, I think, there's been interest in understanding what privacy means for statistical problems. So I'm going to sort of describe this in generality. Now, in statistics, we care about an estimator, theta hat, applied to our data. So here I wrote Z because we're moving towards regression problems where a data set might have X's and Y's. And the goal is to come up with some estimator theta hat, which is close to the true underlying parameter theta naught, at least for a parametric problem. And well, I was told by somebody in computer science that, even though this is a statistical setup, such a perspective was first taken by the computer scientists. But there was a paper which got me very interested in this field from an annals paper from Tony Tai and co-authors from 2021 called The Cost of Privacy. And in that paper, what they want to understand is minimax rates of statistical estimation, where the estimator must be private. So if you look at, minimax rates of, let's say, Gaussian multivariate mean estimation, then you might be used to these sorts of rates like square root of P over N. And that the min is taken over all estimators, the max is taken over the underlying parameter you don't know. Now, if you restrict yourself so that the min is taken over all epsilon delta differentially private estimators, then that's a min over a smaller set. So your min-max rate might be higher, right? And in this paper, in the Annals of Statistics, they actually characterized exactly what the cost of privacy was as a function of epsilon and delta. And you could do similar things since under the Gaussian differential privacy framework. It's just that you would have something that depends on mu. I think it's like mu times n rather than the epsilon and the delta. And this caught our eye for various reasons. So let me first say that that the method that was used for constructing these estimators was based on private optimization, and that's kind of what I'll talk about in this seminar. So the idea is that if you want to calculate some M-estimator by minimizing a function, then in modern statistics you would probably apply gradient descent and go until convergence. Now, if you want to make things private, what you could do is calculate private gradients at each step. And then overall, if on each step you're creating a private gradient, then you're guaranteed that the final output is going to be private. So it seems kind of simple, but the complication is that, as you may remember from an earlier slide, in order for adding Gaussian noise to work, you need some sort of a bound on the sensitivity of your function. So in a lot of the privacy literature, what's assumed is that your data, if you're taking an average, your data are on a bounded domain. Because then there's some bound in the sensitivity of an average. It's that bound divided by n. But if now you're applying this to gradients, well, gradients themselves may or may not be bounded depending on what function you're working with. And so in order to make sure that adding Gaussian noise works, what was proposed in this paper and other related literature is to take your gradient and truncate it at some point, and then add noise that's proportional to that bound that you're guaranteed to have. And the issue here then is that you have this extra tuning parameter of exactly how are you going to truncate your data, which needs to be prescribed or estimated from your data. Okay, so Marco and I come from the robust statistics community, or at least that's what we did some work in the last 10 years or so. And in robust statistics, this idea of M-estimation actually came out of robust statistics. And the idea is that instead of minimizing something like a squared error loss, maybe you should minimize some other function that has robustness properties. And what are the sorts of properties? Well, there's the Hoover loss, which is perhaps the most famous loss from robust statistics. And for the Hoover loss, it's quadratic and then it becomes linear. So another way of looking at it is that the Hoover loss is a loss function that has bounded gradients. And the study of robust statistics is, a lot of it is about what are called influence functions, which have to do with the gradient of your function being bounded. So the idea we had was that, if we have this issue that in order to privatize gradient descent, we need to sort of arbitrarily truncate our gradients, then why don't we just use a loss like a Hoover loss or something with bounded gradients, and then not have to worry about the truncation step at all. So that's what we developed in this work. So to sort of recap this, right, what we're trying to do is look at some sort of an M-estimator where the gradient is bounded. And what we want to do is take these gradients, which are applied to each of the iterates, and then add noise, right? And just to reiterate, so what we're going to end up using is some kind of a composition theorem. So you do something that's private, then you look at your data, and you do something else that's private, and so on. So what's true in privacy is that if you compute a private function of your data, and then you just apply a deterministic function of that, then that's overall going to be private. So there's no loss of privacy by applying more functions. But in this private gradient descent, every time we calculate a gradient, we look at our data again. And that's why we have to be careful about, how much privacy are we, what's the privacy parameter for each of the gradient steps, and how does this accumulate over the course of the optimization algorithm? Yes.
When you say bounded, means that for every theta is bounded in Z, and is the bound itself depending on theta?
No, it shouldn't depend on theta. Yeah. So like the Hoover parameter, right? I mean, it'll just depend on the Hoover parameter. Another question?
Yeah, so what do you mean by loss of privacy?
Yeah, so I mean, what you want to do is you want to see overall what is the privacy guarantee that you have at the end of the day, right? And so the point is like if you're applying these Gaussian differential privacy mechanisms, and you do the first one mu1, mu2, mu3, or let's just say mu, right? So you add the level of noise to guarantee privacy parameter mu. But then now you iterate your algorithms, you do it capital T times, right? Then what you have is the L2 norm of T times of mu. So the overall privacy parameter is going to be T times mu, which is not quite as good as mu, right? Because a bigger privacy parameter means that it's not quite as private. So we just have to be careful how we, well, so the point is that, okay, so in a lot of statistics and optimization research, we care about how quickly the optimization algorithm converges because we want it to converge fast. But in privacy, it's extremely important because the number of iterations we need to take will directly impact what the privacy guarantee is at the end of the day. Okay, so another thing is that, well, this idea of adding Gaussian noise to gradients is something that was also heavily studied in computer science, but in theoretical computer science, most of the previous work just focused on bounding excess risk, which is related to the parameter estimation error, but converting from one to the other isn't completely straightforward unless you assume certain assumptions on your loss. Okay, so here I have sort of a one slide-ish summary of the contributions in this first paper. So what we did was, well, we looked at a low dimensional case, and we looked at, what exactly do you get from looking at noisy gradient descent with these types of robust loss functions? And perhaps not surprisingly, if you know the analysis of gradient descent under strong convexity and so on, right? What we showed was that under log n iterations with high probability, we ended up with these rates, which can also be shown to be minimax optimal. And then we also looked at a second order version. So in optimization theory, well, what you might look at after you look at gradient descent is Newton's method. So Newton's method is something that incorporates information about the Hessian. So instead of just taking a gradient, you take the inverse of the Hessian multiplied by the gradient. And we analyze what a private version of that would look like. Now, when you calculate a Hessian as well as a gradient, you need to privatize both of those. So our method sort of required adding certain noise to the Hessian part and inverting that, as well as adding noise to the gradient. Yes.
So in this case, theta naught, is it the parameter that minimizes? Okay.
Yeah. So you have
True in the, so if you have something like something like regression problem with asymmetric noise and you apply Hilbert loss, then it's not going to be.
Yeah, so we assumed here that you would, you need to have the consistency, so you would need symmetric noise.
So it's basically saying all the parameters that minimize the population version of the.
Yeah, exactly. Yeah. Okay, so in the second order methods, well, as you might know from analysis of Newton's method, right? In the usual analysis of Newton's method, where you don't worry about privacy, you end up with much faster convergence. And we showed that if you add noise to each iterate, then this, well, I mean, what you would hope to happen happens, which is that you can still converge to a small ball of the truth, where the small ball is sort of the order that you would like, but in far fewer steps. Blah, blah. Okay. So, and then one other thing is that a benefit of this robust statistics viewpoint of things is that there are various tools from robust statistics that we were able to bring in. So if you look carefully at the work that preceded us in this area, by Tony Tai and co-authors, what they also assumed was a certain, in addition to being able to calculate, they also assumed a certain bound on the covariance, so the xi's. And if you look at the analog of this in robust statistics, so the Hoover loss is sort of designed to deal with deviations in your y's, if you're looking at a linear regression problem. If you have y deviation in your x's, then in robust statistics this is known as leverage points, and those can really mess things up. So it turns out that just using a Hoover loss isn't actually going to solve all your problems. And instead, what was suggested by the robust statistics literature is to put some kind of a weighting to downweight your residuals when you're minimizing. And what we were able to do was to show that if you use this sort of downweighting, then you don't actually have to assume some a priori bound on your domain, on your xi, which was kind of nice because this is not something that people usually, people usually just assume bounded domain in privacy, in private estimation. Okay, and then the other thing that I'm not going to talk about is that well, it was fairly easy to come up with confidence intervals, at least in the low dimensional case, that were private based on the estimators that come out of this. Okay, so the more interesting thing perhaps is the high dimensional setting. And we haven't yet worked out all the details, so I'll sort of tell you what we have done and then the things that aren't quite as nice. So in the high dimensional setting, if you're doing something like Lasso and you want to estimate Lasso privately, well, there are various optimization methods that people use to minimize Lasso. One example is called composite gradient descent. Right? So for Lasso, you have your quadratic part, which is nice and smooth. Then you have the L1 part that isn't differentiable everywhere. So you can't just use gradient descent. You need to do something a bit more fancy. And one method that's used is to say, well, let's approximate the smooth part of the loss function with a quadratic, and then minimize that plus the L1 norm. And if you write down what the iterates are, it turns out that that it has a nice optimization problem to solve. Furthermore, it has a closed form solution that has to do with soft threshold. Okay, so this is what's done in the non-private setting. And in the private setting, of course, what you expect me to do next is whenever I see a gradient, I'm going to add noise to it. That's what we studied. So we look at these successive iterates, but we're going to apply the same principle that, we look at a loss function with bounded gradients, and then we're going to add Gaussian noise to make sure that all of these gradient calculations are private. Okay, so the requirements are that we have a bound on the sensitivity of the gradients, which is given right here. This capital B will become very relevant in what I talk about. So B is going to be the bound and the sensitivity, and then the amount of noise we need to add will then, of course, be proportional to the bound, as well as inversely proportional to the privacy parameter. Okay, and just as a side note, as I said, these iterates are something that can be easily computed using a method like soft thresholding. So, yes.
Eta?
Eta is the step size.
Oh.
Yeah. Okay, so, right, so the privacy guarantee is kind of straightforward. Because we have a bound on these gradients, we can check that we added the right amount of noise to make each step mu over square root of 2.
B the parameter you choose, or it's given by your estimate?
Yeah, B will be very much related to the estimate. So if you use a Huber loss, it scales with the Huber parameter. Unfortunately, as you will see, B is also going to depend on the dimensionality in a way we would not like. Yeah, so B is something you can compute, but at least in the way that we apply this, it also depends on the dimensionality and not just the Huber.
So the amount of noise that you have in each iteration is the same, right?
Mm-hmm. Yeah.
It just depends on the total number of iterations.
Right, yeah. So the amount of noise, yes. Okay, so
The step size is also.
yeah, the step size is constant here. Yeah. Yeah, I mean, at the the last thing I'll talk about with Frank Wolf algorithm and so on, there are some consideration with different step sizes, but at least for the first and second order, it's the same.
So when you repeat the iterations, the error suppose should be smaller, yes? Or it's-
Yeah. So, I mean, so you converge to,
But otherwise, a few slides before, I feel the bound on the right side, the capital T is on the numerator. Yeah. Why is the capital T is on the numerator?
well, I mean, this is for T on the order of log n. Right, so it's not saying that for every iterate you're getting further away. It's saying that if you choose, I mean, it's basically that we plug in the noise is mu over square root of T. The square root of T pops up there,
Okay.
but our square root of T is like square root of order log n.
So we continue to increase the capital T very low.
No, so I think it will end up sort of being order of log n over n for this last term. And then the other thing is you're not allowed to increase capital T more because then your privacy guarantee is no longer needed. So we sort of program it ahead of time that, and that's why it's important with privacy. It's like you need to know ahead of time how many iterations will you run for. And then that directly goes into at what level of noise are you going to do for each iteration. Yeah. Okay. So right. So for privacy guarantee of this noisy composite gradient descent. I mean, that's fairly straightforward. We choose the amount of noise so that each iterate gives us a mu over root t Gaussian differential privacy. So then if we compose it t times, then we get something that's mu GDP. Okay, and then, well, maybe I won't dwell too much on this slide. So what are the requirements we need on the loss function in order for all of this to work? Well, if you're familiar with the non-private Lasso theory, then generally in order for fast optimization, you need something called restricted strong convexity as well as restricted smoothness. So restricted strong convexity historically is a generalization of the restricted eigenvalue property for Lasso. So that's what you need for small estimation error at the minimum. And then if you want to have fast convergence of these first order iterates, then you also need some smoothness assumption. And we assume the same things for the private version. And then we also assume, since it's high dimensions, that the true parameter satisfies a certain sparsity constraint. So now let's just sort of look at the slide a little bit. So what does the general theorem say? Well, the general theorem says that if the loss function satisfies the restricted strong convexity and restricted smoothness conditions, and your regularization parameters are chosen appropriately, and your step size eta is chosen appropriately, and of course the sample size is large enough, then you end up with a certain guarantee for the last iterate where you go log n time. And that error that you get will be something that depends on n, depends on the bound capital B, which directly feeds into how much noise you added on each iteration, and depends on the low end. Okay. So to sort of piece this together, and I guess that kind of relates to what Stas was asking about, right? So what is the overall estimation error where you're looking at the distance between the global optimum of the population risk function, theta naught, and your iterate theta t, is you'll get this thing, which is sort of the cost of privacy, and you'll add that to the usual parametric rate if we just didn't care about privacy at all, right? So I write slow rate here, or maybe before I go to fast rate, right? So just to tease it apart, if you're looking at something like high dimensional linear regression, then the usual non-private rate you would get is like square root of k log p over n, and then to that you add this guarantee that comes from the previous theorem. All right. Okay, so this is where that part is like, we've written it down, we've proved it, it's fine. Where it gets a little bit more complicated is, so in deriving these results, we sort of felt like actually the rate we would like to have is something that's even faster than what we got in the previous theorem. And I mean, Marco in particular, he's been working on this a bit longer than me, and he's really convinced that instead of r prime, which is a small value, what we should really be shooting for is r prime squared, which is even smaller. But of course, with theoretical statistics, in order to get a faster rate, oftentimes you need to assume things that you may or may not like to assume, and we've kind of been back and forth a bunch of times about what exactly we want to assume. So at least the current version of this that we have looks something like that. So it basically says that if you're willing to deal with a larger sample size, so just in contrast, on the previous slide, I had something like b times square root k over mu. And if in your rate, instead of r prime, we have r prime squared, which is good, but then multiplied by a k. So if we're willing to assume this larger sample size, then we end up with rates that are like r prime squared multiplied by k. So if you look at this, like, in high dimensional statistics, you think, well, that's fine, right? Because I'm willing to pay in terms of sparsity k, as long as p's don't show up. Maybe it's like b squared instead. Okay, but the issue is that the ugly truth is that when we try to apply this to different problems, our b actually has a dependence as square root of p. So this is why we've spent a lot of time trying to improve this, because even if it's not b squared, but it's like b to the 3/2, like it's still, significantly better than b squared when b is like root p. Okay, so let's talk about that a little bit. So here's the ugly truth. So suppose we're doing sparse linear regression. We have IID observations with sparsity level k. Then, as stated here, right, we need to worry about what is this upper bound we have on the gradient of the loss function, and so I had a slide earlier that said that what we need to do is to weight things by something that depends on x in order to deal with unbounded x's. And this calculation spells it out clearly for you, because if you take a gradient of this with respect to the beta, then what comes out is the gradient of the loss, which if you have a Hoover loss, it's something bounded, let's say gamma, but then you also have an xi that comes out. So if you are not assuming bounded xi's, then you really need to do something to control this xi. Yeah, so in order to avoid this issue, then we adopt some kind of weighting. And then the other thing we threw in at the same time was, so this is maybe an orthogonal thing, but since we were building upon robust statistics, like there are ways to deal with not knowing the tuning parameter of your, or not knowing the scale of your noises. So we sort of looked at some optimization problem that cooks everything in. Then I'll show you the loss that we studied. Here's the loss that we studied. If you ignore the sigma for now, right, what we do is we take yi minus xi transpose beta multiplied by w. Okay, so that's to deal with the x's not necessarily being bounded. And then a trick from robust statistics is that if you want to jointly estimate with respect to beta and sigma, then Hooper had a nice formulation of a loss function, which is actually jointly convex in beta and sigma. So if you just took your residuals and divided by sigma, that in itself would not be jointly convex in beta and sigma, but Hooper had a trick to make things jointly convex. So that's the function that we looked at. The loss function is the Hoover loss with some fixed parameter. And then here's the issue, right? So the issue is that what are the right weights to use to multiply by the residuals? Well, in classical robust statistics, the weights that were used look like the minimum of 1 and a constant over the 2 norm max. So this is what you would see in a classical robust statistics textbook. But the problem is that was sort of good in low dimensions. High dimensions need to be a little bit more careful, because if you look at high dimensions, let's say you have x coming from an isotropic Gaussian, right? These L2 norms are going to look like root p. So if you scale by a constant over the L2 norm, then it's just going to squash your problem completely. And this is good from the point of view of the gradients of the loss, but it sort of comes back to bite you when you start talking about the convexity parameter of your loss function. Okay, so the way to sort of deal with these two competing problems was that we ended up saying, okay, choose your weights to scale like square root of p. And then this creates a problem because the b, which bounds the gradients, ends up going like root p. All right. So despite our best efforts, or I should say my best efforts, because I obsessed over this for a very long time, the best I could come up with, I tried rescaling lots of things, was that the bound on the gradient ends up looking like. So now let me plug it back into the theorem and show you. Let me plug it back into the theorem. Let's ignore that. Ignore that. Okay, so we plug it into the theorem and we end up with something like this. I think as a high dimensional statistician, this makes you feel very uncomfortable to put on a slide, because you have this part that looks like a lasso rate, root k log p over n, then you have the part that scales like square root of p. Furthermore, your n has also this. Now, a way of kind of explaining things away is to say, well, okay, so this first term also has the parameter mu. And it might be that if we are in higher dimensions, we're willing to let mu grow with p. I think that's like not totally satisfactory, but it sort of says that as your dimensionality grows, at least the guarantees of our method say that if you let your privacy parameter grow, then you still get same types of rates. But I don't think that's quite satisfactory. The other thing I should say is that nobody knows what lower bounds are. So it's entirely possible that actually some polynomial dependence on p is necessary, but I should also say that so nobody knows in the case when the x's are unbounded what the right rates are. If the x's are bounded, then these problems mostly go away. You don't need to add weights, and this root p won't be there. Okay, so then the other example, which is kind of nice to be able to study in the same context, is, well, instead of doing linear regression, what if we do something like multivariate mean estimation? I'll tell you right now, the punchline is that the rates are no better. You still have this dependence on root p or p, but at least we can study this kind of in the same framework. So in a mean estimation problem, you have this underlying parameter vector beta naught, and you have some noise that comes from a scale family, and let's ignore that. But so So we ended up drawing from a method in robust statistics. So Timothy and Matthew had a suggestion for a type of robust loss that might be used in the case of multivariate mean estimation. And maybe one thing I want to drill through, even if the details are not so memorable, is that things that have benefit or robustness often have benefit also in privacy. So for reasons completely different, this type of loss function was suggested as a robust loss for multivariate mean estimation. And it turns out that if you calculate gradients of this sort of loss function, those are bounded, so we can apply our whole gradient descent framework. So maybe without belaboring the point, the only interesting things to say here are that, well, what are the interesting things? Yeah, so maybe one interesting thing is that if you stare at this carefully, well, you have a Hoover loss applied to a norm. So you have some points where the function is not differentiable. And if you look carefully at the proof, the fact that you have some of these points which are non-differentiable is still okay with the overall flow of the algorithm. Okay, so we end up with rates that also have this dependence on P that are sort of unsavory. So this result is basically the same as what I had with linear regression.
So sparse mean estimation, right?
Yes, this is also sparse mean estimation. Yeah, and again, I don't think anyone knows like what the lower bound should be. Okay, I was going to skip that anyway. So
Would it help if you knew the variance exactly, so you wouldn't have to consider the problems with two nodes?
I don't think it makes a difference. Yeah. Yeah, I think we just said we didn't know the variance just because we could, but I think even if you know it doesn't help. Okay, so now I want to say a little bit about this sort of new ongoing stuff. So I'm very excited about this, but I should also say, I mean, my student Laurencio has been working in this area sort of since August, and we're still going back and forth about like, is it the right formulation exactly? But let me just give you the basic principle. So the principle is that if you're just in like the optimization literature, right, there are all these methods for accelerated optimization procedures. So these are optimization procedures that might converge faster. Maybe it's you have stronger assumptions on your loss, on curvature, and then it ends up leading to faster rates of convergence. And as I said, in privacy, faster rates of convergence are really important because if you have fewer iterations that you require, that means that you can budget your privacy in a way that, it's like mu over square root of t, and that goes directly into how much noise is added on each iteration, hence how much noise you have. So what we ended up looking at is a private version of the Frank-Wolf algorithm. So if you don't remember or haven't seen Frank-Wolf before, this is a procedure for constrained minimization. So you're minimizing some sort of loss function over a constraint set. And generally you take these steps. So the steps are sort of in the direction of some vector vt, but you don't go all the way. And that's governed by the step size a to t. So you calculate these vt's, which are the minimizer of these gradient projections, and you go in that direction. And it turns out that, well, so maybe I should back up a bit. So Frank-Wolf, there was a version of private Frank-Wolf for optimizing a constrained version of the Lasso. And this paper very much motivated our work, right? So the method of private Frank-Wolf is sort of like, well, you take these steps, but whenever you calculate gradients, you add some noise. And the paper on private Frank-Wolf is called Nearly Optimal Private Lasso. So it made us wonder, like, what if you're trying to optimize over other sets, then what sort of rates should you get? And are there ways to speed up what Frank-Wolf is doing? Okay, so the version of Frank-Wolf that we ended up looking at is this sort of, so it's relaxed and it's accelerated. So it's relaxed because whenever we calculate the minimum of a projection of the gradient, right, we allow ourselves to just calculate an approximate minimum. And that's to make room for privacy, because privacy is going to say, well, we're going to add some noise, so we won't exactly minimize. And then the second thing is accelerated. So I think I'll say on the next slide that the usual rates, the usual step sizes that are used to analyze Frank-Wolf are that this step size eta goes down like 1 over t. But it turns out that in optimization theory, there are some breakthroughs in terms of accelerating Frank-Wolf. And under certain further conditions of the loss, which I'll mention in a moment, if you take a constant size step size, then it turns out that you get much faster rates of convergence. So much faster is what you would call in optimization theory a linear rate of convergence. So it's like kappa to the power t. This is how things are shrinking. So that's what we've been trying to look at. So here's a a sort of result. And the result says if you run this sort of private accelerated, there's no privacy yet. If you apply this relaxed accelerated Frankel, then you end up with this sort of convergence where you have something to the power t. But there's one important condition, and this makes things a little bit more interesting. So in order to make this work, you need, first of all, to be optimizing over what's called a strongly convex set. So in particular, this won't work if you're doing Lasso on L1. So we're not claiming to do better than the nearly optimal private Lasso, we're just optimizing over L1. But if you're optimizing over something else, let's say L2, then you can apply this. But you also need a lower bound on the curvature of the loss. So, and if that's the case, then you can get these faster rates of convergence. And this is a somewhat straightforward modification of an argument in a paper that analyzes accelerated Frankel. So all we're doing here is we're saying we relax it a bit because we want to make room for privacy.
So what does this allow us to do?
Well, yeah, stats.
How big would the second term be 3 delta 8 over 2 1 minus kappa?
Yeah, so I didn't write it down. I guess it depends on what eta is. Eta depends on the number of steps there are. Yeah, so that's exactly what will end up with the rates. I think I didn't put them down because we sort of different rates for different settings. So here I've gotten very, very vague about what we did. So what we did was, of course, you know, what are we interested in? Not just some general relaxed version of the algorithm, but adding Gaussian noise. The Gaussian noise depends on how quickly we're going to be converging. And the consequences, which again are still being worked out, right? So the first one is that, so in this paper by on nearly optimal private Lasso that says you should look at the 1/t rates. So they're primarily interested in privately doing Lasso, where you have a quadratic loss L1 ball. But then they have a general algorithm that you can apply whenever you're optimizing over any convex set. The first thing is that if you're optimizing over a set like an L2 ball, then you can get faster rates, much faster rates using our accelerated thing. But then I think the other thing, which I'm still trying to hash out, is the following. So this is quite interesting. One of the conditions I had was that you have a lower bound in the curvature, right? But then if you think about something like, you know, doing linear regression, right? Would you have a lower bound in the curvature, right? Because you're optimizing over this ball, and you'd hope that your optimum is in the ball, in which case you have a 0, like your gradient is 0. So in order to apply this to have the benefits of acceleration, then what we're proposing is that you optimize over a small ball, right? Over a small ball that doesn't contain the true parameter, and then you slowly grow this ball at the right rate. And that allows you to get the benefits of acceleration and still optimize and find the true parameter. And so, I mean, the jury's still out on exactly whether the calculations are correct, but what we think is that it ends up with something like a 1/n⁴ epsilon rate, whereas the existing methods were like 1/n⁵. So, all right, I think that's all I wanted to say. So we kind of, the 3 things I've talked about is that the first one is sort of, you know, nicely written up and packaged that talks about low dimensional. It's sort of the starting point on all of this. High dimensional stuff is kind of still, well, I don't know. I mean, the paper hasn't really gone anywhere in a while. So I think, you know, we have some results that are along the lines of what I've stated, but whether or not they're the best results that could be used within this theoretical framework, I'm not quite sure, because the square root of p and p really bother me. And then in this last part that we're working hard on, I think is part of a much bigger story. So you take your favorite optimization algorithm, it may or may not have an accelerated version, and what mileage can you get? So like specifically in a particular statistical problem like GLM, right? Is there a way to kind of, you know, perhaps slightly regularize the problem so that you can get the benefits from the optimization side and not lose anything statistically? So that's all I have. Thanks for your attention.
I have a question about your comments on this gradient clipping. In gradient clipping, you need to choose the speed, but when you change it to a Hilbert loss, do you also need to choose the parameter?
So that's
So is there a one-to-one map between this clipping threshold and your parameter in the Hilbert loss?
That's why we ended up suggesting that you learn sigma at the same time, because then there's no
Yeah,
learning
otherwise
that
it's
needs to happen.
equivalent.
Right. So when you're joining the estimating over sigma, then that takes away the problem. You just choose your Hilbert loss to be 1, or whatever your favorite thing.
Question for nature. So we consider stochastic gradient descent versus regular gradient descent. That okay, you can use stochastic gradient as a kind of noisy version of the true gradient as well, right? So what would be done with stochastic gradient descent? But
Yeah,
topic has many computational advantages, right?
Yeah. So this is something I'm still sort of working out with my student, because there's quite a bit of work on private stochastic gradient descent, and at least my understanding of it at the moment is that what's bounded is something slightly different than what we're bounding. So I mean, it's some other notion of excess risk. It's like whether it's excess empirical risk or excess population risk. At least this is what my student says. I'm not sure I completely buy that. So yeah, I mean, private stochastic gradient descent is a very important ongoing area that. It's
Yeah,
important.
it seems like it already has built-in noise. It's
Yeah,
just
yeah.
a different flavor, right? Not
Yeah, for sure.
Have another question?
Yeah.
So for, I understand you use a lot of idea from robust statistics to policy. Is there any inspiration you get from BP community to robustness, like going backwards?
I mean, I think I'm still trying to figure this out. Like in my own research, so one thing I'm actively interested in is sort of private estimation on graphs. And that's another place where there have been like separate algorithms proposed in like private estimation versus
In
robust
you can do robust estimation graph.
Right. And I don't think there are sort of direct parallels between methods that have been used. I mean, okay, maybe a better answer. So one thing that got me quite interested in this private gradient estimation was that, you know, these methods of adding noise, they date back to at least 2014 in the privacy. And in the robustness community, this idea of doing robust gradient descent is around like 2020. And as far as I know, the people who wrote those papers had no idea about the privacy, or were not inspired by privacy. So that is one opportunity where privacy could have informed robustness, but didn't.